0.3. So we see that fx is a discontinuous function at the points x equal to 0, x equal to 1 and x equal to 2. So we see that fx is discontinuous at these points, and the function would be non-differentiable at these points because discontinuity implies non-differentiability. Thus we can say that it is not differentiable at the points x equal to 0, 1, 2. Now let's solve another JEE problem. It appeared in 2004 and it says that fx is equal to b times sine inverse of x plus c by 2, x lies between minus 1 by 2 to 0. Fx is equal to 1 by 2 when x is equal to 0, and fx is equal to e to the power of ax by 2 minus 1 divided by x when x lies between 0 and 1 by 2. Now if fx is differentiable at the point x equal to 0 and the modulus of c is less than 1 by 2, then find the value of a and prove that 64 times b square is equal to 4 minus c square. So in this problem we have been given the expression for fx, and it has been given that fx is differentiable at the point x equal to 0. Also given to us is modulus of c is less than 1 by 2. Then we have to find the value of a and prove the relation, that is 64 times b square is equal to 4 minus c square. So for a function to be differentiable, it must be a continuous function as well. So we have already seen that a differentiable function is continuous as well. This is the expression for fx. Now first of all, this function should be continuous. So the left hand limit at the point x equal to 0 should be equal to the right hand limit, and which is equal to f of 0. Now the left hand limit is equal to limit of b sine inverse of c minus h by 2, h tending to 0, and when we put h equal to 0 we get b sine inverse of c by 2. Now the right hand limit is equal to limit of e to the power of ah by 2 minus 1 whole divided by h, h tending to 0. Now what we do is we multiply and divide this expression by a by 2, and so this is equal to limit of e to the power of ah by 2 minus 1 divided by ah by 2 into a by 2. Now this is equal to 1 when h tends to 0. Therefore the right hand limit is equal to a by 2. Also given that f of 0 is equal to 1 by 2. So left hand limit is equal to right hand limit, and that is equal to f of 0. Thus we get b sine inverse of c by 2 is equal to a by 2, which is equal to 1 by 2, and so a is equal to 1. Thus the value of a is equal to 1. So successfully we have solved the first part. Now for the second part, it has been given that fx is differentiable at the point x equal to 0. So the left hand derivative should be equal to the right hand derivative. Now the right hand derivative is equal to limit of e to the power of h by 2 minus 1 divided by h minus 1 by 2 whole divided by h, where h tends to 0. So this is equal to 2 times e to the power of h by 2 minus 2 minus h whole divided by 2h square. So we apply the L'Hopital rule here and get the right hand derivative as equal to 1 by 8. Now we should calculate the left hand derivative. So this is equal to limit of b sine inverse c minus h by 2 minus 1 by 2 whole divided by minus h. Here h again tends to 0. Now we again apply the L'Hopital rule here and get the limit as equal to b by 2 divided by under root of 1 minus c square by 4, or we can write it as equal to b by under root of 4 minus c square. Now fx is differentiable at the point x equal to 0, so the left hand derivative should be equal to the right hand derivative. Therefore b by under root of 4 minus c square is equal to 1 by 8. We square both sides and get 64 times b square equal to 4 minus c square, and this is the relationship we needed to prove. Thus 64 times b square is equal to 4 minus c square, hence proved. Let's solve one more IIT problem. It appeared in 1997, and it is, let fx equal to x into e to the power of minus 1 by mod x plus 1 by x when x is not equal to 0 and is equal to 0 when x is equal to 0. Test whether fx is continuous at x equal to 0, and b part is fx is differentiable at x equal to 0. So in this problem we have been given fx And in the first part we have to test whether fx is continuous at point x equal to 0. In the second part we have to check whether fx is differentiable at the point x equal to 0. So let's look at the solution of this. Given that fx is equal to x into e to the power of minus 1 by mod x plus 1 by x, x not equal to 0 and is equal to 0 when x is equal to 0. Now we see that if x is greater than 0, then mod x would be equal to x. So fx is equal to x into e to the power of minus 1 by x plus 1 by x when x is greater than 0. When x would be less than 0, then mod x is equal to minus x. So fx is equal to x into e to the power of minus of 1 by minus x plus 1 by x, and x is equal to 0, then fx is equal to 0. So it further reduces to fx equal to x into e to the power of minus 2 by x when x is greater than 0 is equal to x when x is less than 0 and is equal to 0 when x is equal to 0. Now we'll check the continuity of fx at x equal to 0. That is the first part. The left hand limit is equal to limit of 0 minus h, h tending to 0, and that is equal to 0. Similarly, the right hand limit is equal to limit of h into e to the power of minus 2 by h, h tending to 0. Now this is equal to 0 because h tends to 0, and also given that f of 0 is equal to 0. So we can say that the left hand limit is equal to the right hand limit is equal to f of 0, and all are equal to 0. So fx is continuous at the point x equal to 0. Now let's check the differentiability of fx at the point x equal to 0. So the left hand derivative of fx at x equal to 0 is limit of 0 minus h minus f of 0 whole divided by minus h when h tends to 0, which is equal to limit of minus h minus 0 whole divided by minus h, h tending to 0, and this is equal to 1. The right hand derivative of fx at x equal to 0 is limit of h into e to the power of minus 2 by h minus 0 divided by h, which is equal to limit of e to the power of minus 2 by h, h tending to 0, and that is equal to 0. So we see that the left hand derivative is equal to 1 and the right hand derivative is equal to 0. That is, the left hand derivative is not equal to right hand derivative, and so we can say that fx is non-differentiable at the point x equal to 0. We see that the LHL is not equal to RHL, but both these are some finite numbers. Thus we can say that it is non-differentiable, but it is continuous at x equal to 0. We say that fx is continuous function at x equal to 0, but is not differentiable at the point x equal to 0. The next part is differentiability over an interval. Till now we have seen how to find the differentiability of a function at any point. Now we are going to see how to find the differentiability of fx over an interval. So let us say that fx is defined in the closed interval a comma b, where the point x equal to a and x equal to b are included. Now fx is differentiable at the endpoints if limit of fx minus f of a divided by x minus a when h tends to 0, and limit of fx minus f of b divided by x minus b when h tends to 0 exist. So for fx to be defined in the closed interval a comma b, it is necessary for fx to be differentiable at the point x equal to a, and it is also necessary for fx to be differentiable at the point x equal to b. So that limit of this expression and the limit of this expression exist, and hence fx becomes differentiable over the entire interval of a comma b. The important points to remember are: always check out the points where the continuity of fx becomes doubtful. So these are the points where we find that fx can be discontinuous, and if a function is discontinuous at some points, then definitely it is non-differentiable at those points. The second is points where the modulus function becomes 0. So if we have any expression containing the modulus sign, then the points at which the modulus function would be equal to 0 are the points at which the function becomes non-differentiable, because at these points there are sharp edges, and hence they become non-differentiable at those points. Let's solve an example. Let fx is equal to maximum of sin x comma cos x, where x is an element of 0 to 2 pi. Check out the differentiability of fx in the given interval. So in this problem we have been given fx equal to maximum of sin x comma cos x, where x lies in the interval 0 to 2 pi. Now we have to check out the differentiability of fx in this given interval 0 to 2 pi. So we first draw the graph of y equal to sin x. This is the graph of y equal to sin x. It is equal to 0 at the point x equal to 0. It is equal to 1 at the point x equal to pi by 2. It is equal to 0 at the point x equal to pi. It is equal to minus 1 at the point x equal to 3 pi by 2. And it is equal to 0 again at the point x equal to 2 pi. Similarly, we draw the graph of y equal to cos x, which is equal to 1 at the point x equal to 0, which is equal to 0 at the point x equal to pi by 2, and so on. Now we have to draw the graph of y equal to maximum of sin x comma cos x. So we see that in this interval between 0 to pi by 4, cos x is greater than sin x. In the interval pi by 4 to 5 pi by 4, we see that sin x is greater than cos x. And we see that in the interval of 5 pi by 4 to 2 pi, cos x is greater than sin x. And therefore, this becomes the graph of y equal to maximum of sin x comma cos x. Thus, we can say that this represents the graph of maximum of sin x comma cos x. So, fx is equal to cos x when x is greater or equal to 0 and less than equal to pi by 4. It is equal to sin x when x is greater than pi by 4 and less than equal to 5 pi by 4, and is equal to cos x when x is greater than 5 pi by 4 and less than equal to 2 pi. Now we see that the doubtful points here are x equal to pi by 4 and 5 pi by 4. So this is the point, that is x equal to pi by 4, and this is the point x equal to 5 pi by 4, which are doubtful because we see that there are sharp edges occurring at the point x equal to pi by 4 and x equal to 5 pi by 4. So let's check out the differentiability at these points. Checking at the point x equal to pi by 4, left hand derivative at x equal to pi by 4 is limit of cos of pi by 4 minus h minus cos of pi by 4 whole divided by minus h tending to 0. We apply L'Hopital rule here to get the left hand limit at pi by 4 equal to minus 1 by root 2. Similarly, we get the right hand limit as equal to 1 by root 2. Thus we see that the left hand derivative is not equal to the right hand derivative, and so fx is not differentiable at the point x equal to pi by 4. Similarly, we check out for x equal to 5 pi by 4 and find that the left hand derivative is equal to minus 1 by root 2 and the right hand derivative is equal to 1 by root 2. Thus fx is not differentiable at the point x equal to 5 pi by 4. So as such, fx equal to maximum of sin x comma cos x is not differentiable at the points x equal to pi by 4 and x equal to 5 pi by 4. Now let us look at the properties of differentiable functions. The first is, if fx and gx are both differentiable at the point x equal to a, then fx plus minus gx, fx into gx and fx by gx when gx is not equal to 0 will be differentiable at the point x equal to a. So it says that if fx and gx both are differentiable functions at the point x equal to a, then the sum of these functions, the product of these functions, or the division of fx by gx when gx is not equal to 0 will also be differentiable functions at the point x equal to a. Let's try to prove this property. Let hx is equal to fx plus gx, where fx and gx are differentiable functions at the point x equal to a. Now the right hand derivative of hx is equal to the right hand derivative of fx plus the right hand derivative of gx at the point x equal to